So we've seen that if there is a changing magnetic flux through a metal loop, there will be an induced current. This means that there must be an electric field present to do the work of moving the conduction electrons in the metal, and the electric field must have been produced by the changing magnetic flux. Now this is true even if there is no conducting loop present, because even vacuum can host an electric field. So this induced electric field then produces the EMF or voltage, and that we can write from our definition of voltage as the integral of electric field E times ds. So that, put together with Faraday's law, means that we can have a very general form of Faraday's law, which is shown at the bottom. So that law simply says that if we have a magnetic field that is changing with time, that is what we see on the right, the d phi dt, that will produce an electric field, and that is the term on the left. So we will see this equation again and look at it in a bit more detail, because this is one of the four fundamental equations of electromagnetism that Maxwell combined from the work of people like Gauss and Faraday, and added in some bits of his own to give a complete description of all phenomena to do with electric fields and magnetic fields. Now to look at something called self-inductance. Now imagine we have a coil with an alternating current flowing through it. The current is constantly changing, so the flux through the coil is also constantly changing. And that means an EMF is being generated across the ends of the coil. Lenz's law says it must oppose the supply voltage causing the current. This process is called self-induction, and the EMF is called a self-induced EMF. So a self-induced EMF must arise in any coil where the current is changing, and it acts to oppose any change in the current. In fact, since any wire that carries current produces a magnetic field, any wire will have an inductance, though it is usually very small unless you shape the wire into a coil. So we make use of this effect when we make a device called an inductor. Now thinking back, you will remember that a capacitor, which we show as parallel plates, can be used to produce a uniform electric field. In the same way, a solenoid, which we will now start to call an inductor, can produce a uniform magnetic field. And just as we were able to define the quantity of capacitance, we can also define a quantity of inductance. So if we have a solenoid of N turns with a current I flowing through it, producing a magnetic flux phi b, then we can define the inductance of that solenoid with the symbol capital L, where L equals N, the number of turns, times phi, the magnetic flux, over the current. Now the symbol for an inductor is that helix shape that represents a coil, and the unit for inductance is the Henry, named after Joseph Henry, a hero of electromagnetic research, though not of good teaching practice. The equation for inductance means that if a solenoid has a large inductance, it produces a lot of flux per unit of current. So, how can we calculate the inductance of a coil? Now we have already derived the equation for the magnetic field due to a solenoid, and we found it was B, the magnetic field, equals mu naught times the current I times little n, and remember that little n was the number of turns per unit of length. So if the total number of turns is capital N and the length is L, then little n just equals capital N over L. So we have B equals mu naught capital N over L times I. Now, from that we can get the flux, phi, which is B times A, because B is a constant throughout this solenoid. And so, using that, we can say that flux equals mu naught N over L times I times A, the cross-sectional area. And then, using our expression for L, the inductance, we have L equals N times phi over current, and that means L equals mu naught N squared A over L. So now we have an expression for the inductance of a solenoid that only depends on the physical properties, So now we have an expression for inductance that only depends on the geometry, the physical dimensions of the coil, just like we were able to find an expression for capacitance that only depended on the area of the plates and the distance between them.